One of the most fundamental concepts that you covered in first year chemistry is the idea of the mole. The mole is based on Avogadro's number, which is 6.0221421 times 10 to the 23rd. Oftentimes it's just shortened to the idea of 6.02 or 6.022 times 10 to the 23rd. And what that is that's based on the number of atoms that are present in 12 grams of pure carbon, and it should say pure carbon 12. So there is an experimental basis for the idea of Avogadro's number. And this right here is Avogadro. He's an interesting looking fella. He looks kind of shifty right there with that eye. But the idea of the mole is really, really important. So let's go ahead and spend a little time reviewing it. Okay, so the first idea is that the mole is exceptionally large. Okay, it is so large that it is hard to deal with the idea of the mole with normal sized objects. And so the idea of this is stacking a mole of papers. So, a paper and then a paper and then a paper. Your average size book is going to be something like between 500 and 1,000 pages for a textbook. You may have one that's larger than that. But for a mole of paper stacked up, it'll go all the way to the sun and back almost 2 billion times, so it's pretty ridiculous. A mole of marshmallows, not the mini marshmallows, but the regular sized marshmallows, okay, would cover the earth 12 miles thick. Okay, and then this is a fun one for you guys to kind of think about. If you have a mole of pennies and you distribute it to everyone on Earth, and that's all, 8 billion people, that it would allow you to spend $1 million an hour every day for your entire life. And that does not include sleeping. You'd have to spend the money while you were sleeping as well. And then a mole of blood cells is more than all of the blood cells in every human on Earth. So the mole is an exceptionally large number. The only way that it makes sense to talk about the mole is when we're talking about atoms and molecules. If you look at it on a realistic life-size object scale, there's no way that you could look at it in terms of the mole. So you need to be able to go from numbers to moles and moles to number. And the conversion to go from numbers to moles is done using Avogadro's number, as you see here. If you see I have atoms, okay, I can convert between atoms and moles. 6.022 times 10 to the 23rd of anything is a mole of anything. So for example, if instead of atoms I said basketballs, then I could say that there are 6.022 times 10 to the 23rd basketballs in 1 mole of basketballs. And then I'd have 871.8 moles of basketballs. Okay, it doesn't matter what the unit is, as long as you are consistent throughout. So for here it says 1.25 moles of carbon. It could easily say something like C2, and you could say 1 mole of C2, and then this wouldn't be atoms anymore, this would be molecules. So as long as you are consistent that the conversion factor between 1 mole of anything and that number of things is the idea of 6.022 times 10 to the 23rd. Going from grams to moles requires that you do the formula or atomic weight as the conversion, and that's why we spent a little bit of time talking about it earlier. It's the idea that that gives you the conversion factor. So here I'm in grams of CO2. If I take the gram formula mass of carbon dioxide, that right there represents the conversion factor between grams and moles. So to go from grams to moles, you use the idea of atomic mass or gram formula weight, however you want to say it. There's a million different ways of saying it. So let's look at some molar conversions. And it says combining gas chromatography with mass spectrometer. No idea what that is, and it doesn't matter. All it does is says allows investigators to detect 0.25 picograms of cocaine. Okay, that right there is the amount that forensic investigators can detect whenever there's any sort of crime or something along the lines. It's a very, very small amount. It says how many cocaine molecules must be present to be detected. So we start off with the idea of we have 0.25 picograms of cocaine. And we're just going to say COC. Now, the thing that we need to do is we need to go to the gram formula mass. But before we do that, we need to realize that we're in picograms. So picograms is one of the things that was not on your list. So it's not something that you're expected to memorize right off the bat. But you should get familiar with the idea that a picogram or a picometer is 1 times 10 to the minus 12th. It's, 3 below what a nano is. So now we're in the idea of grams. So now I need to go from grams to moles. And the idea is I need to go ahead and take these numbers, C17, H21, NO4, and I need to figure out what the gram formula mass is for that. And it ends up being about 303.35. And you should be familiar with gram formula mass enough to be able to figure that out. Once you are in moles, you have to go to the number of molecules that are present. So if you say 1 mole of COC ends up being 6.022 times 10 to the 23rd molecules of COC. And if you look, you went from moles to moles. This is in grams to grams, picograms to picograms. So if you look, that thing all cancels out, but what this ends up being whenever you multiply everything out is it ends up being about 4.96 times 10 to the 8th molecules, which is an incredibly small amount, especially when you consider the fact that in a single milliliter of water, you're talking about trillions of times that. So let's go to the next example. The next example says determine the price of gold per atom if it is $42.85 per gram today. So we start off with the idea that you have $42.85 per 1 gram. So now we want to go from the price per atom. So we say, okay, we look at gold. We find gold in our periodic table, and we see that the atomic mass of gold is 107.87 grams for 1 mole. If I were to stop right there, that would give me the price per mole of gold, but that's really not what I want to do. What I want to go ahead and do is I want to go all the way from moles to atoms. So you'd say 1 mole is 6.022 times 10 to the 23rd atoms. And when you finish multiplying this thing out, you end up with a pretty ridiculous number, which is 7.676 times 10 to the minus 21st, and that's your price per atom. And it is an extremely small value, but the reason why is whenever you think of gold, you're thinking about a tangible physical amount of gold that you can actually see. And when you talk about individual atoms, that's just not the case. So although this price is a little bit ridiculous, it does make sense with what we know.